Hello, and welcome to my presentation on the nitration of phenanthrene. My name is Landon Hardee, and I'm a junior here at Francis Marion, and I've been doing research with Dr. Briana Aguila from the chemistry department. So one major issue that a lot of developing countries face today is availability of clean drinking water. We already have technology today that can accomplish water purification. However, on a large scale, it can be expensive and difficult to distribute from a logistical standpoint across all of these different countries. Therefore, we want to look for other means of purification, but these means must be cost-effective, easily distributable, and they still must be effective in the removal of target compounds from water. So recently, researchers have been investigating the use of what are known as covalent organic frameworks, or COFs. And what these are 3D molecules that can be designed to sequester certain target compounds from their environment. And this does have implications for use in water purification. And one of these compounds the compound that has been looked into recently as used as a COF is phenanthrene. And in order for phenanthrene to be used as a COF, it must first be nitrated. And phenanthrene is what is known as a polycyclic aromatic hydrocarbon, and it is composed of 3 fused benzene rings. And the structure of phenanthrene can be seen can be observed in figure 3.1. So we were able to successfully nitrate the phenanthrene, and over 9 separate runs, where in each run we used 2.12 grams of phenanthrene, and this was dissolved in 14 milliliters of acetic anhydride. So with strong stirring and while on ice, because this reaction does tend to be fairly exothermic, we added 4 milliliters of 50-50 nitric acid to sulfuric acid, slowly dropwise over the course of about 10 minutes. And then after the addition of the acid, each reaction was allowed to stir for the appropriate amount of time, as seen in figure 1, at room temperature. Once the reaction time was up, the mixture was then poured directly into ice water, as phenanthrene tends to be fairly insoluble in water, and then it was able to be vacuum filtered, and the product was weighed. And the final yield can also be found in figure 1 for each of the 9 runs. So looking at figure 2, we can see the color change across the 9 separate runs. And for this particular presentation, we want to focus on run number 4. In figure 3.1 and 3.2, we can see that the expected NMR data suggests that the ideal tetra-substituted product for phenanthrene shows peaks in the 9.7 to 10.2 range, and this would be in figure 3.2. The NMR data that we obtained, which is in figure 4, shows that there is a shift from about 8.9 in starting phenanthrene, which is the blue on top, to approximately 9.6 in run 4, which is the red lines on the bottom. And what this indicates is that an electronegative group has been added on, and electronegative groups can deshield hydrogen atoms, and the more deshielding or the more electronegative groups, the farther left on the graph we're going to see peaks. So also looking at IR data that was obtained for phenanthrene from the product in run 4, this is in figure 5, we can clearly see asymmetric nitrogen to oxygen stretching in the 1500 region, as well as symmetric nitrogen to oxygen stretching in the 1300 region in run 4, where compared to pure phenanthrene, which don't have these peaks present. So the IR data, in addition to NMR data, suggests that an NO2 group is present in the final product. However, based on NMR data, comparing the expected versus the observed shifts, we can confidently conclude that only one nitrate group is present per molecule, which is not ideal. So, in summary, we were able to successfully nitrate phenanthrene via the direct addition of mixed acid solution to dissolved phenanthrene. And results from the expected NMR data compared the experimental NMR data indicate that the ideal product of a total of 4 nitrate groups was unable to be obtained. And being that run 4 resulted in better NMR data as well as IR data across the 9 runs, this suggests that reaction time does not play a significant role in the degree of nitration for phenanthrene. So looking ahead, we do have plans in place to further investigate how to increase the degree of nitration for the method that I laid out previously. So we do want to acknowledge the Francis Marion University's REAL grant for helping to fund us, and I appreciate you listening to my presentation.